So for our first example, suppose that we have 7 full wine bottles, 7 half full bottles, and 7 empty bottles, and we would like to divide the 21 bottles among 3 individuals so that each will receive exactly 7, and additionally, each individual must receive the same quantity of wine. So, as normal from linear programming, the first question we ask is, what do we want to know? In this problem, we want to know how many bottles will each individual get and of what type, or how many bottles of each type will each person get. That is what we want to know. Let's translate that into our decision variable. We let xij be the number of bottles number of bottles of type I meaning either half, full, or empty. Number of bottles of type I that person J being person 1, 2, or 3 will get. Again, what we want to know how many bottles of each type will each person get. Next is our goal. Our goal is to either maximize or to minimize a certain value, but in this case, we just want them to follow all the constraints. We don't maximize or we don't minimize anything. Therefore, we can just set an arbitrary objective function of max z being an arbitrary variable. We just have to make sure that all of our constraints are followed. Or let's now construct our constraints. For our first constraint, we would like to divide the 21 bottles among 3 individuals so that each will receive exactly 7. So this just means that each person should get a total number of bottles of 7 bottles each. Let's model out the number of bottles that person 1 will get. So that will be xf1, the number of full bottles he will get, plus xh1, the number of half bottles he will get, plus xe1, this should be equal to 7. Similarly, we should be able to do for person 2, xf2 plus xh2 plus xe2 is equal to 7, and for person 3, xf3 plus xh3 plus xe3 is equal to 7. Next constraint that we will be formulating is that there are 7 of each bottle that is available. So there are 7 full, 7 half, and 7 empty bottles. To do that, let's just go. Number of full bottles is xf1 plus xf2 plus xf3 is equal to 7. Number of half bottles is xh1 plus xh2 plus xh3 is equal to 7. And xe1 plus xe2 plus xe3 is equal to 7. That is the number of empty bottles available. Next constraint that we want to formulate is that each individual must receive the same quantity of wine. So, regardless of how many bottles they receive or the types of bottles that they receive, each individual must get the same amount of wine. So, to construct that, person 1 will get xf1. That's the number, or that's the amount of full bottles of wine that he will get, plus 1 half xh1. That's the amount of wine he will get from a half bottle, plus 0 xe1. That is the amount that he will get for an empty bottle. Since this is 0, we can just remove this constraint overall and just say that this is the total amount of wine that person 1 will get. This should be equal to the amount of wine that person 2 will get. Therefore, we have equals xf2 plus 1 half xh2, and also should be equal to the amount of wine that person 3 will get. So that's xf3 plus 1 half xh3. We've already written down all of our constraints, or at least our technological constraints. Don't forget your non-negativity constraints. So that's xij is greater than or equal to 0 for all values of ij. And lastly, since these are bottles, and bottles cannot be halves or they cannot be 1/4, we have to take note that all bottles are integer. Therefore, we say that xij is integer. This constraint makes our problem an integer. Of course, this is how we just write it in formulation, but in the software, they would read it differently, or we have to code that each variable is an integer. Let's now solve example number 2. Gotham City Police have just received 3 calls for police. 5 cars are available. The distance in city blocks of each car from each call is given below. Gotham City wants to minimize the total distance cars must travel to respond to 3 police calls. This is actually an example of an assignment problem wherein we have X tasks and Y workers, and we want to know what's the optimal assignment for a certain task to a certain worker. So in this case, our tasks are the 3 different calls, but we have 5 different workers, which are your 5 different police cars. And our goal is to minimize the distance traveled, the total distance traveled of the police cars. The assignment problem actually introduces us to a new variable, which is what we call a binary variable. A binary variable, given by the name binary, only takes the value of 1 or 0. And this binary variable gives us actually flexibility to solve a lot of different problems, which we will see later on in our next examples. Usually, binary variables are used to denote either a yes for 1 and a no for 0. This is the most common, but it can be flipped otherwise. But the yes or no problem, or the yes or no variable, actually opens us to solve or formulate or mathematically model out a lot more different problems, which we will see later on. So for this case, we will just say that the binary variable xij will be equal to 1 if car I is assigned to call j. I will be 1 to 5, denoting our cars, and j will be 1 to 3, denoting our calls. So the variable means that x11 will be, if this is equal to 1, this means that car 1 will be assigned to call 1. If x21 is equal to 0, then that means car 2 will not be assigned to call 1. Alright, given those variables, it's now time to formulate our objective function. Again, the goal is to minimize the total distance. Therefore, it's going to be min z is equal to 10x11 plus 11x12 plus 18x13. This allows us, or this tells us, that if car 1 is assigned to call 1, it will be traveling a total distance of 10. Because this part of the objective function will have a value of 10 times 1. That is if x11 is equal to 1. However, if x13 is equal to 0, this means that car 1 will not be assigned to call 3. This will get a value of 18 times 0, which means that the total distance, which was not traveled, will not be taken into consideration into your optimal z value. Okay? Then we just continue on, plus 6x21 plus 7x22 plus 7x23 dot dot dot. For the interest of time, I will just do the last 3 plus 9x51 plus 4x52 plus 7x53. Let's now formulate your constraint. Our first constraint is we have to have at least one car assigned per call. One car assigned excuse me, per call. To note that, it's that x11 plus x21 plus x31 plus x41 plus x51 is equal to 1. And we want exactly 1 to minimize the problem. This constraint denotes that for each call, there has to be exactly one car that will attend to that call. So if x11 becomes a value of 1, given the constraint should be equal to 1, all the other values will then be equal to 0, meaning that if car 1 is assigned to call 1, cars 2, 3, 4, and 5 will no longer be assigned to call 1. Similarly, if x21 gets the value of 1, all the other values will be equal to 0, which means that all the other cars will not be assigned to call 1. We now copy the same constraint for call 2 and denote that x12 plus x22 plus x32 plus x42 plus x52 is equal to 1. And for call 3, x13 plus x23 plus x33 x43 x53 is equal to 1. The other set of constraints is that one car can be assigned to at most one call. We say at most because it's possible that a car may not be assigned to a call since there are more cars to a call. To denote this, car 1 can be assigned to call 1, or car 1 can be assigned to call 2, or to call 3. The maximum value is 1, so that each car will only be assigned one call, or it can have a value of 0, which means the right-hand side should be a less than or equal to 1. This means that if car 1 is already assigned to call 1 and gets a value of 1, the other two will automatically get a value of 0 since the maximum value is 0. But it's also possible that all three of them have a value of 0 and it's still less than or equal to 1, meaning car 1 will not be assigned to any of the calls. We just copy the rest of the constraints for the other cars. x21 plus x22 plus x23 is less than or equal to 1. Interest of time, I'll do the last one. x51 plus x52 plus x53 is less than or equal to 1. Those are all the important constraints, and now our technological constraints. Let's not forget your non-negativity constraint, xij greater than or equal to 0, or we can just say that xij is binary for all values of ij. There you have it. assignment problem using a binary variable. Okay, for the next example, we will show you another use of the binary variable. Now, this binary variable, the use of the binary variable here, allows us to limit some constraints or to limit activity or to limit the activation of a certain number of constraints. Let's take 3a for example. Suppose that the mathematical model fits linear programming except for the restrictions that only one of the equalities below or one of the inequalities below must hold. So here we will use a binary variable to denote if constraint 1 or constraint 2 will hold, meaning it is an active constraint or it is a valid constraint. And if since only one is an active constraint, the other constraint should not be an active constraint, or we're going to try to force it to become a redundant constraint. So we do this by introducing a binary variable. Let y be equal to 1 if constraint 1 holds, and 0 if constraint 2 holds. Notice that this is only either a yes or no, either or constraint. To do this, we're going to use the big M. Again, M in IE41 is a very big number. Big M, big Miko, M, because I'm big. Just kidding. But we're going to use the big M to force a constraint into a redundant constraint if that constraint quote unquote does not hold. So we do this by adding M to the side that is of greater value. So on the first constraint, we add an M. So again, we add M on the side that has a greater value of the constraint. Therefore, on the first constraint, we add it on the right. And on the second, we add it on the left, since the greater than side is on the left side of the second constraint. The question now is, what should be the coefficients of M, or of the very big number? So we do this. Notice again that we let y equal to 1 if constraint 1 holds, which means if y is equal to 1, constraint 1 should be an active constraint and constraint 2 should be a redundant constraint. So we model this out so we do this in constraint 1 by adding a coefficient of 1 minus y to M, and to constraint 2 adding the condition y, or the coefficient y. Why is this the coefficients that we add? Again, remember, it's y is equal to 1 if constraint 1 holds. Let's try and investigate what happens. If constraint 1 holds, y is equal to 1, and the corresponding value becomes, or the corresponding constraint becomes 3x1 minus x2 minus x3 plus x4 is less than or equal to 12 plus 1 minus 1, since y is equal to 1, m. Or basically, this becomes 0m, or basically just removes out the m value, or you keep your first constraint as is. While the second constraint becomes my plus x1 plus x2 plus x3 plus x4 is greater than or equal to 15, or it's simply a very big number is greater than or equal to 15. If we simplify this into a second graph, that constraint will be a very big number is greater than or equal to 15. It will be somewhere here, way above your feasible region, and it becomes a redundant constraint. Therefore, this constraint does not hold. The second constraint will not hold, but you keep the first constraint. Alternatively, if we do, let me just erase some parts. Alternatively, if if constraint 2 holds, y is equal to 0. What will become, or what would be your constraints are 3x1 minus x2 minus x3 plus x4 is less than or equal to 12 plus 1 minus 0m, or this becomes m, and my, since y is equal to 0, that becomes 0, x1 plus, let's just write that down for illustration, my plus x1 plus x2 plus x3 plus x4 is greater than or equal to 15. But since y is equal to 0, this becomes 0, you basically have your original second constraint left. So in this case, we are able to model out that only one of the constraint holds if 1 minus y, sorry, we are able to model out that only one constraint holds if y is equal to 1, then we keep your first constraint and the second constraint becomes redundant. If y is equal to 0, the first constraint becomes redundant and we keep your second constraint. We now look at example B or problem B. It holds except for the restriction that at most two of the following three inequalities hold. So example A is what we call an either or constraint. And example B or problem B is an at most constraint. This time, it will be different. It's not now, since it's not an either or, meaning one constraint is true and another constraint is false. This time they can be true, true, false, true, false, false, true, 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 false, true, or what have you. We model it quite differently. In example A, the condition is dependent on the other constraint. In this case, each constraint is technically independent of each other, but at most two of the following three inequalities must hold. So what we will do is we introduce a binary variable, let yi be equal to 1 if constraint I holds, 0 otherwise. So if constraint 1 holds, if the first constraint holds, y1 will be equal to 1. If constraint 2 holds, y2 will be equal to 0. Constraint 3 holds, y3 will be equal to 1. So again, as we said, we employ the big M and add it on the side that is greater. In this case, all of them on the right side. But again, constraint 1, constraint I, if that constraint holds, therefore we model it out as 1 minus y1 for constraint 1, 1 minus y2 for constraint 2, and 1 minus y3 for constraint 3. And again, similar to the first example, if a constraint holds, the coefficient of m becomes 0, and we transport back to the original form of the constraint. If it doesn't hold, you have an expression that is less than or equal to a very big number m, which makes it redundant and therefore makes it not hold. But we have an additional constraint that at most two of these holds, or that at most two of these constraints hold. Therefore, we must say that between y1, y2, and y3, this cannot have a value more than 2. So that at most two of the constraints hold. It means if y1 is 1, y2 is 1, y3 will be forced to take on a value of 0. Constraints 1 and constraint 2 are the only ones that hold. Or if y1 and y3 is 1, y2 automatically gets a value of 0. So therefore, we only get two constraints holding. But it's also possible that only one of them will be equal to 1. For example, y2 is 1 and the other 2 is equal to 0. It still fits your constraint that at most two of them will hold. That's how you model out an at most type of constraint. The next application of the binary integer problem, or the binary integer or binary variable, is what we call your longest root or shortest root method, or your network problems. In this case, we are asked to determine the longest route from point A to point B, and this is a longest route problem. So what do we want to know here? We want to know the path we want to take. So we let xij be equal to 1 if the path from node I to node j is part of the longest route. To illustrate, if xa1 is equal to 1, this means that this path is part of the longest route. If x24 is equal to 1, that means that this path is part of the longest route. Now for the objective function, since we're looking for the longest route, it will become a maximization problem, and we want to maximize the distance traveled. So the distance traveled from node A to node 1 is 4, so that's 4xa1 plus 6xa2. The distance traveled from node A to node 2 plus 6x13 plus 2x14 dot plus 6x3b plus 2x4b. So again, if xa1 is a path, this gets a value of 1, and the value of 4 times 1 is part of the longest route distance. And if x14 is not part of the longest route, it becomes 0, and the distance does not contribute to your longest distance. For the constraint, what we do is that for each node, we just do in minus out. In node A, there is no in, but there has a path has to come out of node A. So we say that 1 is equal to xa1 plus xa2. And that way, we are sure that the path will start. Next, for node 1, again, that's in equals out. All nodes coming in are in node 1 are a1 and 2, 1. And the nodes coming out of node 1 are 1, 3 and 1, 4. Again, that's in equals out. Therefore, in xa1 plus x21 is equal to x13 plus x14. That means that if a path goes into node 1, you are sure that a path will also go out of node 1. If no path comes in node 1, no path should also come out of node 1. Let's go now to node 2. Node 2 in is xa2. Out is equal to x21 plus x24. Node 3 is in x13 plus x43 is equal to x3b. Node 4 in x14 plus x24 is equal to x43 plus x4b. And node B in is x3b plus x4b is equal to 1, so that we are sure that the path ends. And of course, your binary constraints. Xij is binary. Now, if this becomes a shortest route problem, just change max to a min.